name is Tommy, and today we're talking about photoelectron spectroscopy. Now, for sodium, the electron configuration is 1s2, 2s2, 2p6, 3s1. So, what I did was that I just kept on going through these terms until the exponents, or the superscripts, reached a total of 11, because 2, 4, 10, 11, if you add up 2 plus 2 plus 6 plus 1. Now things get a little trickier for Na plus 1 because it's an ion, and it doesn't have as many electrons, because we removed one for it to become more stable. So if this was the electron configuration of sodium, sodium plus 1 would be 1s2, 2s2, 2p6, but no 3s1, because that electron was removed for the thing to become more stable. Now this actually shares an electron configuration with neon, and can also be put in as, if we go back to the regular electron configuration, there's also something called noble gas configuration, which is basically electron configuration, but it takes out that part that's shared by the noble gas. So in this case, this is shared with neon. So instead of putting this, we'll put in brackets Ne, and then put 3s1, and that still signifies sodium. Now for this problem, we're given a PES graph, and for a part, we have to write the suborbitals represented by each peak. So this peak here is the first two electrons, 1s2, in the first energy level. This peak is 2s2, this is 2p6, 3s2, and this, we kind of have to judge off the relative heights of everything else, is 3p5. So as you can see, you kind of just do it as you normally write it, going along the bars until you reach the last one where you have to judge its height with everything else to get your number, where if this is 6, we can tell that this is 5. And another thing, because this is 2, based off of the first 2 electrons being in an orbital, we know that this must be 2p6 because 1, 2, 3, 3 times 2, 6. So now that we have this, we have to identify the element, which is part B. And the element here is chlorine, because we have 4, 10, 12, 17, and the element with atomic number 17 is chlorine. And now, for part C, if the element gained an electron, draw another peak representing where that peak would be. And if it gained an electron based off of binding energy, binding energy would decrease. Because we're adding an electron, and it kind of spaces all the other ones out, causing the binding energy to go down a bit. So not only does it go up further, but the binding energy also decreases, so we draw it to the right. Now, if it were the element next to it, what would happen is that the peak would actually go a little bit to the left. Sorry, that marker doesn't work very well. And the reason for that is because you're adding more protons. So this would be argon, for example. This would be argon. So you're adding another proton and the attractive force would increase. So when you added another peak, this time it went to the left of the other one because binding energy increased because charge increased.